In this video, we're going to talk about the binomial distribution. In particular, we're going to talk about the normal approximation to the binomial distribution. And to motivate this topic, let's consider the following example. Suppose you have a loaded or cheating coin, so that means it's not a regular fair coin, and the probability of landing heads is 0.36. So that's why it's not a fair coin, because the probability of landing heads is 0.36. Say you throw this coin 100 times. What is the probability that you obtain more than 51 heads and at least 51 heads? So to solve this, let x be the number of heads in 100 tosses of the cheating coin. And we know that x follows a binomial distribution with parameters n equal to 100. And probability of success in this case is 0.36. And therefore, the probability that you get k heads in 100 tosses is 100 choose k, 0.36 to the power of k, and 1 minus 0.36, which is 0.64 to the power of 100 minus k. So then the probability for A, you get more than 51 heads is probably you get 52 heads plus probably you get 53 heads, and so on, all the way up to probably get 99 heads, plus probably you get 100 heads. Man, there's 48 terms here you have to add up. And that's too long, right? Too long to calculate, especially for a midterm test or final exam, or even a assignment. So what do you do here? Well, we're gonna need the binomial approximation to the normal distribution. Sorry, approximation of the normal distribution to the binomial distribution. So why is this so? So let me just bring up the following. Let's consider the binomial distribution. Okay, so if n equal 10 trials, and again this is our cheating code, probability of success is 0.36. As you can see, this is what the distribution looks like. Let's increase the number of trials to see what happens to the shape of the binomial distribution as we increase the number of trials to 20. Okay, so this is, we increase it to 20. Let's double it now to 40. So this is our binomial distribution for the cheating code. Okay, so let's say we increase it to 40, yeah, from 20. See what happens. Okay, there you go. And then let's increase it from 40 to 80. See what the binomial distribution looks like. Increase it to 80. But what do you notice? So as you increase the number of trials of the binomial distribution, then the binomial distribution looks more like the normal distribution. So in fact, as the number of trials increase, then you can approximate the binomial distribution with the normal distribution. And the precise theorem of this fact is stated as follows. So suppose x is originally a binomial distribution with parameters n and p, and suppose this criteria is satisfied, that n times p is greater than 5 and n times 1 minus p is greater than 5. If these two assumptions are satisfied, then x is actually approximately normal, with mean mu given by mu equal to n times p and variance given by n times p times 1 minus p. That is, you can approximate the original binomial distributed random variable by a normally distributed random variable with mu and sigma squared equal to these two. Okay, so in our case, we can apply it here to our problem of calculating probability of landing 51 heads. So note first that we need to see these two criteria satisfied. N times P and N times 1 minus P is given 5. Let's check N times P here is 100 times 0.36, which is 36, which is certainly greater than 5. How about N times 1 minus P? Well, here is 100 times 0.64, which is 64, which is also greater than 5. So therefore, we can approximate the binomial distribution by the normal width. So that means, in fact, that x is approximately normal, right? With mean mu equal to n times p. In this case, we already calculated that to be 36, and variance given time n times p times 1 minus p, which is 36 times 0.64, which is 23.04. Okay. So therefore, the probability that we get more than 51 heads of this unfair coin is, okay, so now we're going to need what they call a continuity correction, which I'll talk about in the next slide. So this only happens when you go from a discrete random variable, when you approximate a discrete random variable by a continuous one. In this case, you have to add a 0.5 because it's a greater than. I'll explain that again in the next slide. So in fact, we're looking at probably that x is greater than or equal to 51.5. And since x is approximately normal, then to calculate this normal probability, we standardize it, which means we change it to a standard normal variable by taking away the mean and divide by the standard deviation. So then once we plug the right hand side into the calculator, we get 3.22, and looking at the normal table, 3.22 is here, 0.00064. So what's this continuity correction that we've been talking about? Well, it basically outlines the rules from when you approximate a original discrete random variable by a continuous random variable. So this is what we're doing here, and this is the first rule which we use, where we have a greater than, right? A greater than, like here. And so the rest of the rules goes as follows. If we have probably x greater than or equal to a discrete probability, then going to the continuous one, you have to take away 0.5. When you're calculating the probability that x is less than a, then the continuity correction is minus 0.5. If you're calculating less than or equal to a, then you add 0.5. So those are the rules. So let's calculate. This is our A solution. Right? Remember, we also have a B question where we want to calculate the probability that you land at least 51 heads of the unfair coin. So here, the continuity correction by our rules is minus 0.5. So minus 0.5. So let's calculate probability that x going to 50.5. And again, we standard normalize to get 50.5 minus 36 square root 23.4. Put that into the calculator. We get, looking at the standard normal table, which is what you should know how to do. This is 0.00126. And you can try some of these other problems at home. This is our x represents our 100 tosses of the unfair coin with probably 0.26 landing heads. So for example here, I'll just, you can do the calculation with the continuity correction, right? Then you want to calculate the probability that x is less than or equal to, we have the minus 0.5 here, 44.5, right? By our, yeah, oh sorry, add 0. So add 0.5, so it's 40, 5.5, sorry. And similarly, you'll see the continuity correction is minus 0.5. So it's 44. There you go. Okay.